Hey guys, today we're going to talk about the ideal gas law. Super excited to share that with you. And then we'll do a whole bunch of fun stuff in class to unpack that ideal gas law. First, let me get my screen up and running here. Um, Good. Okay, so ideal gas law. In order to jump into ideal gas law, we need to go back to some of those previous laws that we learned before. Oops. There we go. They deal with those laws that we learned before. Specifically, these would be something like Boyle's law, and then Charles' law. Now, what Boyle's and Charles' law mentioned, remember that Boyle's law states that the volume of a gas is inversely proportional to the pressure of a gas. Right? So we learned that in this equation. So P1V1 equals P2V2. But we could also express that since it's inversely proportional, we could say that the volume is inversely proportional. And there's this little it's kind of like a little chopped up infinity sign, right? All that means is that it's proportional. It's inversely proportional. So 1 over P. Okay. So P1V1 equals P2V2 is another way of saying that V is proportional to 1 over P. Okay. Charles' law, if you'll recall, states that there is a direct link between V and T. So they're directly proportional. So we saw this as V1 over T1 equals V2 over T2. Sorry. Tilting a little. Okay, so V1 over T1 equals V2 over T2. But when we say they're directly linked, they're directly proportional, that also means that we would say that V is proportional, there it is again, right, to T. Okay. The last thing that we learned about was Avogadro's law. Avogadro. Okay. And this also stated that the volume was directly proportional to the amount of moles of gas. Okay. So directly proportional to the amount of moles of gas, which we'll represent by N. Okay. So volume is inversely proportional to pressure, directly proportional to temperature, directly proportional to moles. This is only true if you have a consistent amount of, this is true if only you have a consistent amount of temperature and moles. This is true if you have a consistent pressure and moles. This is true if you have a consistent pressure and temperature. Now, what we can do is we can rewrite this as V is proportional to T N over P, right? That's combining all of these guys together. Okay, V is proportional to T times N over P. Now, if we can establish this proportionality as a constant, if we can express that proportionality as a constant, let's call that R, right? We would get V times R, or is proportional by R, to T times N over P. Okay. What that means then is if we multiply P by both of these things, right? And this leads us to our famous equation, PV equals NRT. Okay? That's the derivation for PV equals NRT. This is what's known as the ideal gas equation. All the ideal gas equation states is that ideal gases have this relationship. They're related by this. Okay? In this case, again, P is equal to pressure, V is equal to volume, N is equal to the amount of moles of the gas. R is a constant known as the gas constant. And then T, of course, is temperature. Okay. You will get this equation for any subsequent exams, right? But just wanted to unpack that equation. So this is the ideal gas equation. Again, I want to emphasize this. This emerges out of Boyle's, Charles, and Avocado's law. And importantly, it doesn't mean that all gases behave according to PV equals nRT all the time. It's just that that gases ideally behave according to this relationship. Okay. And the degree to which they relate to this relationship, the degree they are ideal gases. Now, I want to spend a little bit of time real quick on this R, this gas constant. Okay. Because the gas constant, remember we talked last time about how different, there are different kinds of units for pressure, right? And there's different kinds of units for temperature, right? So 1 atmosphere is equal to something like 760 torr, which is equal to 760 millimeters of mercury, right? Those are very, very different numbers, 1 and 760, right? Okay. And so what that means then is this number, the proportionality constant, the gas constant, that's going to change depending on the type of units that you're using. Now, for the purposes of our discussion, there's only two really important ones. Actually, really, there's only one. And that is if you're using liters, atmospheres, moles, and Kelvin. Okay. If you're using those units, then your gas constant is 0.8206. I'm sorry, 0.08206. Okay. 0.08206 liters times atmospheres per mole times Kelvin. Okay. So that means if you're ever working with PV equals nRT, okay, if you're ever working PV equals nRT and you want to use this constant, you have to make sure that your volume is in liters, your pressure is in atmospheres, you're working with moles, and that your temperature is in Kelvin. Okay. There are a bunch of other there are several other forms of R, but we're not going to be really using any of these. So just there's only one gas constant I want you to focus on, and that's this guy right here, 0.08206. Okay. Let's go through. Let's see. Let's keep going here. Let's see. Yeah. I want to emphasize a couple things. This is going to be a little bit of a hodgepodge of concepts today, guys. Okay. Note, right? Well, actually, note this. So, yeah, we'll just leave it there like that for right now. Let's go through what a practice problem would be. So let's say that I had, if I was curious about the volume of a given gas, and you had 2 atmospheres of pressure, right? And then you had 32 grams of O2 gas, right? And then you had 25 degrees Celsius, right? And then let's see. Yeah. And then I was asking you to find the volume. Okay. Well, then I would just simply rearrange this equation to solve for volume. So I would go PV equals nRT. Solving for volume gives me V equals nRT over P. Okay. And then I can start plugging and chugging. So I have the pressure, which is the 2 atmospheres. So that doesn't change. The 25 degrees Celsius, remember that has to be converted into Kelvin. So you add 273.15 to that. That should give me 298.15. We have our gas constant, which I mentioned a second ago. Let me scroll down so I'm not blocking this. We had our gas constant, which is 0.08206. Move this to the side here. And then we have are moles. Okay. Now I gave you 32 grams of O2. Each oxygen molecule has an atomic mass of 32, right? So that means I just have 1 mole. Okay. So I'd multiply these guys out, and that would give me my volume. Okay. So that's one key way that we can utilize PV equals nRT, just plugging and chugging. There are some instances where you'll be given a descriptor like standard pressure and temperature. You'll see something like STP or standard temperature and pressure. That represents what would be 1 atmosphere. And then it would be, hang on one second. Now my laptop's being very silly. 1 second. Nope. It's not working. Come on. It's not working. Okay. I think it's working now. Maybe it wasn't. It was always working. Never mind. I don't know. Hopefully it's working now. Okay. So sorry, standard temperature and pressure. This would be instances where you have 1 atmosphere of pressure and the standard temperature is 273.15 Kelvin. Okay. So if you ever see something in like homework, or if I ever give it to you in an exam, it's asking for standard temperature and pressure, and you're trying to solve for volume or something like that. Whenever a standard temperature and pressure, assume 1 atmosphere of pressure, and then 273.15 degrees Kelvin. Okay, so that's like the intro to PV equals nRT, but PV equals nRT is actually really useful for a bunch of different ways, not just in solving for each of these particular variables. We can actually utilize it to solve for density, which is kind of dope. I'll show you what I mean in a second here. Okay, so let's take PV equals nRT again. Where is my cursor? So PV equals nRT. If we rearrange this equation, right, and we take the pressure, keep the pressure here, and divide both sides by RT, and then we take the N and divide it by the volume. Okay, so all I did is I pushed the volume underneath here and then pushed the RT and put them underneath here, right? If I do that, right, and we keep in mind that the moles times the molecular mass, if you recall this, moles times molecular mass is equal to grams, right? If I take this number and multiply it by the molar mass of a gas of interest, I end up with grams over volume, which is the definition of density. Okay. So not only can we utilize PV equals nRT as a way of determining what any of those 4 variables that we described are, right? But we can also use PV equals nRT as a way of solving for density in 2 different ways. We can either take N over V times the molecular mass equals density, or since N over V is equal to, excuse me, P over RT, we could also do it this way. P over RT times the molecular mass is equal to density. Okay, so those are 2 ways that we can calculate the density of a gas, right? By rearranging PV equals nRT and then multiplying it by the molecular mass of a gas. Okay. In a question like this, you would be given like the identity of the gas, and I would say, all right, here, and I would either give you the moles of the gas and the volume of the gas, or I would give you the pressure and the R and the T of the gas, right? In either case, you get the identity, and then you just multiply the molecular mass of that gas by either N over V or P over RT, and then you'll have the density, which is pretty straightforward and pretty cool. The other big thing that we can do with this is we can start to click it into balanced chemical equations. Okay, and the reason why is now we have a way of figuring out, now we have a way of determining the amount of moles of a thing, right? PV equals nRT allows us to figure out how many moles there are of a given gas, right? By measuring these other different characteristics. Okay, and so what we can do is we can ask questions like, let's see, here's a good one. This is from the slides. All right, and we'll walk through this. So let's say that I have a set chemical equation. So let's call it 2NaN3 reacts to 2Na plus 3N2. Okay. The molecular mass of Na is 65. Then the molecular mass for nitrogen is 28. Okay. Now let's say this is actually a very common chemical reaction that we utilize in synthesis of an airbag, right? So you have, this is called sodium azide, right? This is these sodium azide. What it'll do is it'll rapidly degrade in order to form nitrogen gas. Okay. So in the event of a car crash, right, what's going to happen is there's going to be this rapid breakdown of the sodium azide to form a certain amount of gas. Now, actually, this is kind of important because if you have too much sodium azide, let's draw a person driving a car. Anyway, they're driving the car. It's a box car, you see, with a weird, it's probably made by Tesla. Just look at that. Anyway, let's say I didn't add enough grams of sodium azide, right? That means I wouldn't make enough gas, right? So when the airbag comes out, it wouldn't be enough to stop the person from bonking their head on the front of the dashboard, right? On the other hand, if I added too much gas and if I add too much sodium azide and I make too much gas, it's going to shoot out way too much and then pop this person's head backwards, right? So instead, what you have to do is you have to add the exact amount of gas to make the desired volume, the exact amount of sodium azide to make a desired volume of nitrogen gas, okay? So let's say then that I want to fill a 36-liter airbag with N2 at 1.15 atmospheres of pressure. Okay. Let's assume that this temperature is going to be relatively hot. So let's say the temperature is 299 degrees Kelvin. Now what I want to do is ask how many grams of sodium azide do I need to add in order to fill up an airbag with these characteristics? And this has to do with this has to do with nitrogen gas here, okay? So how do we go about solving something like this? So the way we tackle this is we understand we're trying to figure out grams of sodium azide, okay? But we have all this information about a nitrogen gas airbag, okay? With these variables though, with these numbers though, we can start to figure out how many moles of nitrogen that would be, right? And we utilize PV equals nRT, right? Let's rearrange to solve for moles of nitrogen. So that would be N is equal to PV over RT, okay? Now, if I do that and start plugging things in, I have a pressure of 1.15. I have a volume of 36, right? I divide that by my R, which is 0.08206, right? And then we have our temperature, which is 299, all right? If I plug all these things together, so I plugged in P and V and R and T, this will give me the total amount of moles, which in this case is 1.69 moles. Okay. That tells me the amount of moles of nitrogen that I need to have in order to have an airbag that is 36 liters at an atmosphere of 1.15, given 299 Kelvin as a temperature. Okay. So I need 1.69 moles of N2. Now, some of you in the comments are already going to be like, wait, Dr. K, I know where this is going because this has to do with what we did back in exam 1. And you're 100% correct, right? Because if I have 1.69 moles of N2, the next step is I need to convert that into moles of sodium azide. And the way I do that is with our balanced chemical equation. So I'm trying to convert from moles of N2 to moles of sodium azide. So I take the coefficient of what I want to turn it into, which is sodium azide, that's 2. That's this guy right here, divided by the coefficient of where we're coming from, 3 in this case, because we're coming from nitrogen. If I multiply that by 1.69, that'll give me 1.13 moles of sodium azide. Okay. We're not quite done, but we're almost there. That's how many moles of sodium azide I need. The last thing that I need is grams of sodium azide. And remember, in order to convert from moles to grams, you do moles times molecular mass equal to grams. Okay. Our molecular mass for sodium azide, I gave you that earlier. That's 65. That totals up to 73.5 grams of sodium azide. Okay, so let me do this in reverse. If I took 73.5 grams of sodium azide, converted that into moles of sodium azide, use this balanced chemical equation to go from moles of sodium azide to moles of nitrogen to calculate out the amount of moles of nitrogen, then I could use that to make a prediction as to, or that would be the appropriate amount of moles in order to make an airbag with these characteristics. These ones, that is. Okay. So not only can we use PV equals nRT to just solve for P or V or N or R or T, right? Not only can we utilize PV equals nRT in order to solve for density in 2 ways, both of which you should know, 1 and 2, but we can also utilize it in conjunction with a balanced chemical equation in order to solve for grams of reactant, grams of product, whatever the case may be. Okay, so PV equals nRT is a super equation. We utilize it all the time. And yeah, so definitely something to have locked in. I'll get a worksheet going for you guys for tomorrow. And then I think we should be squared away. But other than that, that's all I have for you guys today. I'll see you guys tomorrow. Dr. K out.